Hello everyone, I'm Tsai from National Taiwan University. Today I'm going to present a paper titled Superb SG Enhanced Speech Processing Universal Performance Benchmark for Semantic and Generative Capabilities. This work is done by several members from different institutions. I will first talk about Superb and our motivation. Next, I will introduce each of the tasks in Superb SG and how we design them. We will provide the benchmark results and analyze about the Superb framework. Finally, we give the conclusion in our future work. So, what is Superb? Superb is a universal performance benchmark for self-supervised learning models or SSL models in speech. Last year, Yang and other researchers introduced Superb. They create a standardized framework to evaluate the SSL models from different perspectives. This framework has been already tested on various tasks with more than 10 SSL models. Here is the big picture of Superb framework. It contains two main components, which are upstream and downstream. Upstream transforms the raw waveform into representations, and downstream takes the representations as input to do the downstream task. Superb collects the most famous SSL models into upstream, and downstream contains tasks covering four categories, which are content, semantics, speaker, and paralinguistic. To make Superb affordable to all the participations, the upstream models are frozen to avoid fine-tuning, while a weighting sum mechanism is used to fully utilize the upstream across different layers. With Superb, we could easily benchmark the SSL models with different perspectives. Our motivation is that tasks in Superb are too easy and generative tasks are missing. We all know that BERT and GPT series achieve SOTA in many challenging tasks in NLP, while they are also self-supervised learners who learn from large task corpus. Then how about these learners who learn from speech? Do they know the meanings of an audio recording? Can they generalize well on other languages? And how about the capability to generate new speech signal? In Superb, they evaluate the semantic and content capabilities with only simple tasks, and generative tasks are not included. Thus, we introduce Superb SG to enhance Superb for semantic and generative capabilities. We introduce speech translation into semantics, all of domain ASR into content, and unlock a new category, which is generative, and include voice conversion, speech separation, and speech enhancement. We provide the benchmarking results and analyze the reliability and robustness of Superb framework. After introducing Superb SG, the downstream contains 15 different spoken language tasks in 5 categories. We hope that this work could give us more comprehensive understanding about self-supervised learning in speech. Let's talk about our design of task. First, we introduce speech translation (ST) into semantic task, which generates the translation of a speech directly. This task is much like machine translation, but now the input is speech. The semantic information is important in this task since the translation has to contain the same meanings as speech but in different languages and modality. We choose Covo ST2 English to German dataset for training and testing. A 3-layer encoder-decoder transformer with a convolutional subsampler is used as our downstream model. We predict character level translation and train by label smooth cross-entropy loss. Boot score is used as our evaluation metric. Next, we introduce out-of-domain automatic speech recognition (OOD-ASR) into content task. It transcribes a speech in an out-of-domain scenario, while self-supervised learning models are trained by clean speech corpus in English, such as LibriSpeech or LibriLite. We transcribe the speech with different accent or in different languages to test the model's capability across different domains and languages. We consider Spanish, Mandarin, and Arabic from Common Voice and spontaneous English from Santa Barbara corpus. Our downstream model is a 2-layer by LCM which predict the character level transcription. We train this task by CTC and evaluate by averaging the word error rates across the dataset. For the generative task, we first include voice conversion (VC). It aims to convert speech from an arbitrary speaker into a given one, while keep the content unchanged. In Superb SG, we conduct voice conversion under any-to-one setting and evaluate the speaker transferability and generalizability. We use the intralingual any-to-one VC dataset in Voice Conversion Challenge 2020 and use Tacotron 2 as our downstream model. We train the model to reconstruct the acoustic feature by L1 loss, and hi-fi gain is used as our vocoder to generate final waveform. 3 evaluation metrics are used in this task. Male septron distortion, MCD, is used to measure the signal quality. Automatic speaker verification accept rate and vowel error rates are computed by off-the-shelf models to evaluate the correctness of speaker and content. Next, we introduce speech separation, SS. It aims to separate multiple source speech from a mixture of speech signal. We introduce this task to evaluate the generative capabilities when input contains multiple speakers. We investigate this task with LibreMix dataset under mixed clean condition with 2 speakers. 3-layer BioCM is used as our downstream model to predict the signal mask for each speaker. The output waveforms are generated by masking the input signal with predicted mask and transform back to time domain. We train the downstream model to minimize the L2 distance between the ideal mask using permutation invariant training, which is PIT, and SISDRI is used to evaluate the performance. Finally, we introduce speech enhancement, SE. SE aims to remove background noise from a degraded speech signal. We include this task to evaluate the generative capabilities under noisy conditions. We discuss the speech enhancement problem on the voice bank demand corpus. A 3-layer BioCM is used as our downstream model, and the model is trained to predict the signal mask for the clean speech. We minimize the L2 distance between the ideal mask and evaluated the speech quality by PESQ and STOI. Let's see our benchmarking results. We benchmark 14 SSL models with Super SG, and traditional acoustic feature FBank is also included as our baseline. First, on the speech translation and off-domain ASR, all the upstream models outperform FBank baseline. It shows that SSL models actually have semantic capabilities and could generalize well on other languages and domain by learning from English speech corpus. However, on generative tasks, SSL models are not always outperform FBank, which are colored in red. On speech separation and speech enhancement, FBank perform better than half of the SSL models. This phenomenon shows that the knowledge learned with self-supervised learning algorithm didn't give much advantage to speech generation. Among the upstream models, WAV2, VAC2, and Hilbert generalize well on all the tasks, and on speech translation and off-domain ASR, they outperform other SSL models with a large margin, which is aligned with the conclusion in Superb, while on generative tasks, their improvements are limited. Next, let's talk about our analysis about the Superb framework. To be a practical benchmark, the evaluation results should be reasonable and stable. In this section, we want to answer the following 2 questions. Are the benchmarking results reliable, and is Superb framework robust? To answer the first question, we analyze the correlation of the performance between downstream tasks. To give a more general conclusion, we bring back 6 tasks in Superb to cover all the categories. They are phonic recognition and ASR from content, intent classification from semantics, speaker identification and automatic speaker verification from speaker, and emotion recognition from paralinguistic. We expected that the tasks requiring similar information should be highly correlated. We analyze the correlation between tasks in following 3 steps. First, we change the performance metrics into a higher beta manner. Next, we compute the Spearman's rank correlation coefficient between each pair of tasks based on the performance. If a task is evaluated by multiple metrics, we compute each of them separately, since they evaluate the performance with different perspectives. We visualize the correlation using heat map and it is obvious that some patterns exist on the map. To make the results more clear, we further cluster these tasks using k-means. Finally, we rearrange the heat map by the clustering result, and it is clear to see that the tasks in same cluster actually share some common properties. With the correlation analysis, we show that the benchmarking results are aligned with our common understanding and confirm the reliability of Superb. Next, we answer the second question: is Superb framework robust? We do this analysis by trying different downstream architecture as well as dataset and see whether our conclusion is still the same. First, we train the downstream task with a larger and a smaller model, and the result shows that the benchmarking results are agnostic to downstream architecture. We also run the experiment with different amount of training data, which are 10%, 5%, and 1% of original training dataset. Generally, the benchmarking results are still agnostic to training dataset size. Combined with the conclusion on architecture, we confirm the robustness of Superb framework. We summarize the contribution of Superb FG in conclusion. Superb FG enhances Superb by adding new tasks in semantics and content, and unlock a new category, which is generative. We provide the benchmarking results of Superb FG and confirm the reliability and robustness of Superb framework by our analysis. All our experiments are open sourced and reproducible on S3 PRL repository. For our future work, we will keep increasing the diversity and difficulty of Superb and give a more comprehensive understanding about the capability of self-supervised learning models in speech. We will also test the Superb framework under low resource conditions, which are more difficult but more efficient and eco-friendly. Thanks for your listening and look forward to the new results.